Hello everyone, check the description to know about my bundle offer. MIT researchers developed a photon shuttling interconnect that can facilitate remote entanglement, a step toward a practical quantum computer. Quantum computers have the potential to solve complex problems that would be impossible for the most powerful classical supercomputer to crack. Just like a classical computer has separate yet interconnected components that must work together, such as a memory chip and a CPU on a motherboard, a quantum computer will need to communicate quantum information between multiple processors. Current architectures used to interconnect superconducting quantum processors are point-to-point in connectivity, meaning they require a series of transfers between network nodes with compounding error rates. On the way to overcoming these challenges, MIT researchers developed a new interconnect device that can support scalable all-to-all communication, such that all superconducting quantum processors in a network can have communication directly with each other. They created a network of two quantum processors and used their interconnect to send microwave photons back and forth on demand in a user-defined direction. Photons are particles of light that can carry quantum information. The device includes a superconducting wire or waveguide that shuttles photons between processes and can be routed as far as needed. The researchers can couple any number of modules to it, efficiently transmitting information between a scalable network of processes. They used this interconnect to demonstrate remote entanglement, a type of correlation between quantum processes that are not physically connected. Remote entanglement is a key step toward developing a powerful distributed network of many quantum processes. The research appears in Nature Physics. The researchers previously developed a quantum computing model which enabled them to send information carrying microwave photons in either direction along a waveguide. In the new work, they took that architecture a step further by connecting two modules to a waveguide in order to emit photons in a desired direction and then absorb them at the other end. Each module is composed of 4 qubits, which serve as an interface between the waveguide carrying the photons and the larger quantum processors. The qubits coupled to the waveguide emit and absorb photons, which are then transferred to nearby data qubits. The researchers use a series of microwave pulses to add energy to a qubit, which then emits a photon. Carefully controlling the phase of those pulses enables a quantum interference effect that allows them to emit the photon in either direction along the waveguide. Reversing the pulses in time enables a qubit in another module any arbitrary distance away to absorb the photon. However, transferring a photon between two modules is not enough to generate remote entanglement. The researchers need to prepare the qubits and the photon so the modules share the photon at the end of the protocol. The team did this by halting the photon emission pulses halfway through their duration. In quantum mechanical terms, the photon is both retained and emitted. Classically, one can think that half a photon is retained and half is emitted. Once the receiver module absorbs the half photon, the two modules become entangled. But as the photon travels, joints, wire bonds and connections in the waveguide distort the photon and limit the absorption efficiency of the receiving module. To generate remote entanglement with high enough fidelity or accuracy, the researchers needed to maximize how often the photon is absorbed at the other end. They used a reinforcement learning algorithm to pre-distort the photon. The algorithm optimized the protocol pulses in order to shape the photon for maximal absorption efficiency. When they implemented this optimized absorption protocol, they were able to show photon absorption efficiency greater than 60%. This absorption efficiency is high enough to prove that the resulting state at the end of the protocol is entangled, a major milestone in this demonstration. In the future, they could improve the absorption efficiency by optimizing the path over which the photons propagate, perhaps by integrating modules in 3D instead of having a superconducting wire connecting separate microwave packages. They could also make the protocol faster, so there are fewer chances for errors to accumulate.